看见了吗？有一双眼睛，穿透星际气体和尘埃组成的巨大谜团，注视着银河系中心。在那里，无数恒星围绕着超大质量黑洞翩翩起舞，不停转圈的轨迹如同太空之花。100年之前，广义相对论预言了黑洞的存在。100年之后，是它让人们第一次确信超大质量黑洞。与黑洞捕手 Reinhard Genzel 一起看穿天体。
Dear viewers, ladies and gentlemen, I would like to invite you today to take a trip with me, a trip through the universe. I'm an astronomer and astrophysicist, and you will see that as we in astronomy explore the universe, it's a bit like going through a forest. You go into the forest, you admire the wonderful trees you've never seen before. You see flowers, red flowers, blue flowers. And so much of what our exploration, of course, brings us to new ventures, new stories. Then we would like to understand how the forest works. And we discover that the blue flowers are only on the left side of the path. Why is that? So that's the part of astronomy which has to do with physics. Now the story which I will tell you about today has taken quite a while, 40 years for me, and I'll like to give you a little travel report. Now, our universe is full with objects we call Milky Ways, like our own Milky Way, which of course you know, if you have a dark sky in the summer, you look up there, you see the band of the Milky Way. The Milky Way is a so-called spiral galaxy. It's a flat system which is rotating. Our sun is in the outskirts of our own Milky Way, about 27,000 light years away from the center. As you see in this picture, there are spiral arms. These spiral arms have stars in them. The whole Milky Way has about 100 billion stars. That's most of the mass of the Milky Way. But there's also some material between the stars. We call that interstellar gas and dust. In fact, that is very important for forming new stars out of the interstellar material. And that's going to be a very important part of this story, is the center of our Milky Way, which is of great interest to us astrophysicists. Now, before we go into the details of what we are trying to explore, how we have done it, and what we have found, I'd like to start first with a little movie which gives you a sort of a prescription of what you will encounter in this trip we are taking. You'll see we fly through the Milky Way, you'll see the stars, you see dust and gas clouds, as I just described, and then finally we end up in the center. Let's talk about the physics behind all of this. Our Milky Way, of course, relies on gravity. Gravity is a force between two bodies. That was known to human mankind. We studied the solar system, and Tycho Brahe and Kepler in the 17th century, Galileo, all understood that if you have a mass like our sun and planets which are attracted by that sun through gravity, then they can orbit. They can go around the sun and orbit. Now in 1915, Albert Einstein proposed a more mathematical formulation, a wider formulation of this phenomenon of gravity, which we call general relativity. General relativity adds this force between objects to the evolution of the motions, and also takes into account that not only masses like the sun and the planets and so forth interact with each other, light does too. And I'll explain a little more a little later. So in 1915, we had all of a sudden a mathematical formulation of a broader class of descriptions of gravity, which actually includes also the fate and evolution of the entire universe on large scales. Only 1 year later, Karl Schwarzschild, in the top of this picture, published the first solution of this complicated mathematical equation. And in the next 50 years, others like Roger Penrose, Roy Kerr, Stephen Hawking, and others perfected this mathematical exploration of this new phenomenon, the new phenomena in general relativity. Now, one of the predictions of general relativity, as I already said, is that photons or light particles also feel gravity, which is certainly not what Newton would have thought. So if you have the Earth and you have the sun in front of us, and you look at a star behind the sun, then in this picture here, the light from the star behind the sun gets bent toward the sun, and then when we look at the sun, the light of the star appears to come from up rather than straight behind the sun. This effect of light bending was predicted by the theory, and in 1919, only a few years later, there was a solar eclipse in the middle of the Atlantic Ocean, and the physicists from the United Kingdom went there and observed stars behind the eclipsed sun, the moon in front of the sun, and measured the positions of stars very accurately in this situation when they are behind the sun. And they knew, of course, these positions very well when the sun was not there. And they found that the prediction by general relativity was exactly right. So that was a triumph of a new theory, made Albert Einstein a very, very famous man instantaneously. So that's a very important thing. We know that gravity is something which pulls us back if we jump from the surface of the Earth. Now, if we think of the sun and we want to launch a rocket from the surface of the sun in our mind, then you can calculate from Newton's equations that you need a speed of about 600 kilometers per second in order to escape the gravity of the sun and go into outer space. This finding in Newton's theory is dependent on the mass of the sun. The larger the mass of the sun, the more gravity, but also on the size of the sun. So if you make the sun in your mind smaller, then in fact gravity gets stronger. So in your mind you could imagine another sun which is much, much smaller, only 3 kilometers in size, and then you will find that the rocket, in order to escape, would have to have a speed of 300,000 kilometers per second. Now that is the speed of light. Now we know from numerous famous experiments that the speed of light is, so to speak, the highest speed of communication in our universe. Nothing can move as fast or faster than the speed of light, which has mass. So that means that if you look at this fiducial sun, if you make it still a little smaller, the escape speed would still be larger. That means that a region surrounding this object, which we call the event horizon, is decoupled from the rest of the universe. Even light cannot escape, and surely not a rocket. So that's the concept of what we now call a black hole. There's another property of such objects we call black holes, which are predicted by Einstein's theory, and that is the fact that if you turn the rocket around and fly to the center, then once you're inside the event horizon, you cannot, of course, communicate back home, and within a finite time, you will end up in the center. Everything will end up in the center. And that means that at the center of such a black hole, all the mass should be within a point. and therefore the mass density is infinite. That we call a singularity. That's a strange prediction. Is it really true? We don't know, because of course we cannot go to the center of a black hole. So that was general relativity in theory, but the question now is, do these objects really exist? And if they do, how would you find them? If they don't shine, because they are black holes, how would you see them? Well, we see them by the action of gravity. Think again of the sun and this other solar system where the sun is so small that it is a black hole, but otherwise has the same properties, the same mass. And in this case, let's assume the same planets. Then of course the Kepler's laws, which tell us that the innermost planets move faster than the outermost planets, and that the speed of motion around the sun goes like 1 over the square root of the distance, that's still true, even if you have a black hole. So that's basically how we make black holes visible. We use the action of gravity itself onto other objects in the vicinity to test how much mass there is, and then also how compact the mass is, and whether or not it must have the properties of a black hole. So in a short introduction, that's sort of the technique we're using nowadays to hunt down black holes. Now, the first evidence that such objects actually might be realized in the universe came in the 60s. Then the radio astronomers began looking at the sky and mapping out the radio sky, and they found sources which were very bright in the radio bands, but very faint little smudges, stars on optical plates. But then when you look at the detailed spectrum of these stars in the optical, so you disperse the light and you look at the different colors, then you find that there are sharp spectral lines which are very well known in terms of their ratios, hydrogen, helium, neon, and so forth. But all these lines are redshifted by 16% relative to what we would find in our laboratory on Earth. Now, Martin Schmidt, who made these experiments with the big Palomar telescope in California, then concluded that probably this redshift must be due to the expansion of the universe. So everything which is far away moves away from us and thereby induces a redshift. And the further away an object is, the larger the redshift is. In this case, 16% means that this little smudge there is 2.4 billion light years away from us. Okay, 2.4 billion light years away is nowadays not such a large distance. At the time in the 1960s, it was a sensation because that little smudge of a star actually has 1,000 times more energy output, luminosity, than our entire Milky Way. And that comes apparently all from a little compact region. How could that be? Well, said some, one solution is there's a black hole. But wait a second. You said black holes can't radiate. Well, if you have a big black hole and it attracts material from the surroundings, then this material, whether it's gas or stars, will move inwards, radially but also more likely in a plane, spiraling inwards into the black hole. But before it disappears in the event horizon, it is not seen anymore. Before, on the outside of the event horizon, it converts its gravitational energy into heat and radiation. And that process, actually, you can show theoretically, is 100 times more efficient than the process of fusion, which is how the sun is working. You convert hydrogen by fusion into helium and other elements. 100 times more efficient and almost so efficient that you can take a significant fraction of the rest mass, as we say, mc squared, of a particle and convert it to radiation. So that's a tremendous paradox. On the one hand, we say we can't see these objects, or rather the region inside of the event horizon, but on the other hand, obviously, they seem to be generating a lot of radiation. But now comes the question, that's a nice hypothesis. In science, a hypothesis is only a starter. Now you have to use experiments to verify or not verify this hypothesis. How could you verify that these quasars indeed are black holes? Well, I've given you a little bit of a hint already by using motions of objects in the vicinity, but these quasars are too far away. So two British theoreticians, Donald Lindenbell and Martin Rees, in 1971, wrote a very influential paper saying, well, if there are such black holes which fuel and power quasars, maybe these black holes also exist in other galaxies, not just in this very few quasars. And maybe they're everywhere. And indeed, that's what we nowadays believe, that every galaxy has in its center a massive black hole. And the evolution of galaxies and the evolution of black holes are tightly linked over the cosmic evolution after the Big Bang occurred about 13.7 billion years ago. So how would you then test this if you can't test it in quasars? Well, you want to go to the nearby galaxies, and the closest galaxy we have is our own. So the idea is find test particles in what we think is the center of our galaxies, see how they move, and whether there is a concentration of mass which points in the direction that there might be or must be a central black hole. This kind of work started in the 1970s and then 80s. There is one technical issue because of the dust and gas, which I introduced earlier in the talk. You cannot really see the center of our galaxy from our position on Earth in the visible. The dust basically blocks out all the visible radiation. You have to go to longer wavelengths, what we call infrared waves or even radio waves, in order to see the center of our Milky Way. There it is. That's a center of few light years with a modern telescope in the infrared, and you see it's an enormous concentration of stars. About 1 million times larger concentration than in our solar neighborhood. So at night, if you were an Earth in this region, at night the sky would be bright, very, very bright. So that's the region where you want to hunt. And how would you hunt? Well, the radio astronomers looking at the same region found a very compact radio source. So compact that its size is a mere 40 microarc seconds. That's about 20 centimeters on the moon. And that fits the bill. That would be the size, roughly speaking, of the region around the event horizon of a few million solar mass black hole. Now, there's not only stars and radio emission, there's also gas in the central region. The pink stuff is ionized gas, and the green stuff is neutral gas. And so the testing of whether or not there might be a mass started off by looking with spectroscopy in the infrared at this region and look at the Doppler motions of gas. The Nobel laureate Charles Townes, who won the Nobel Prize in 1964 for the invention of the laser and the maser, in his later years, when he moved to California, to Berkeley, had a group of students and postdocs. I was one of them. And we looked at this region and looked at the motions of these gas clouds and found that if you plot the mass on the vertical axis versus the distance from the center of the radio source, then while on the outside at large radii, the mass changes. That is, the mass is extended due to the stars themselves. But when you go inside of about a few light years, the mass does not change anymore and makes up a few million solar masses. So by the mid-80s, our group in Berkeley was fairly convinced. Here we are, here we have the first empirical proof for the existence of such a massive object, such a massive black hole, as discussed by the discoverers of the quasars and predicted by general relativity. Is it true? It might be, but some of our colleagues felt not at all convinced, because they felt gas is not a very good tracer of gravity. Gas can be pushed around by magnetic fields or winds from stars. Much better to use stars. Another thing is the distance of a few light years is about 1 million times the event horizon size. So you're way outside a region within which you would have to suspect is the mass of such a black hole. So there could be other things fitting in there, like a cluster of 1 million neutron stars, or other faint stars which you cannot see. So we had to replan, if you like. I moved to Germany and built up a new research group at the Max Planck Institute for Extraterrestrial Physics. We built new equipment which allowed us to see the motions of stars with precision. So lots of technology, new detectors had to be built, big telescopes came into place in order to then measure the motions of the stars. Another second group in California, headed by Andrea Ghez and her colleagues, started the same experiment a few years later with a big telescope, which is on Mauna Kea, the Keck telescope. So we were working with the European Southern Observatory in Chile, and they were working in California and in Hawaii. And so if you look at the picture, the image of the central light month, which is this circle centered on the radio source, Sagittarius A star, which is this little yellow cross, then you can see the motions of stars by putting different years in different colors. Year 1, red; year 2, green; year 3, in blue. And you see immediately with your eyes that very close to the radio source, the stars are moving. How fast? Well, 100 times as fast as the Earth around the Sun, on scales of only, say, 1 light year or less. So again, you can calculate from that how much mass there has to be, and you find it's the same few million solar mass which we had a decade earlier with gas, but now we have it with a very reliable tracer. But must it be a black hole? Well, we're still about 100,000 times the event horizon size away from the black hole, so you could still imagine some even not very likely configurations of that mass, which is not a black hole. So the hunt goes on. We have to go to higher resolution. Instead of measuring on average the velocity of stars, we began to imagine, could we perhaps find a star which moves very fast, comes very close to the black hole, and so we can actually trace in detail its orbit. And indeed, nature was good to us, which you cannot always hope in exploring the universe. It's not a laboratory which you can rely on or build things. But here we are. Nature gave us a few stars, in particular this one here, which comes as close as only 17 light hours of the radio source. 17 light hours is about 5 times or 4 times the orbital radius of the planet Neptune around the Sun. And it moved there when it came as close as 17 light hours in the year 2002. It moved there with a speed of about 2.5% the speed of light. That's incredible. Nobody had seen such large velocities, and it implies indeed immediately, without much analysis, that the mass, the same mass of a few million solar masses, has to be now located within this 17 light hours, and that made other solutions very unlikely. Another important point here to demonstrate is our measurements, the ones with the Chilean telescopes in blue, and Andrea's measurements with Mauna Kea in red agree perfectly. That's very important for science. You can say whatever you like, you only will be believed if the experiment can be repeated. And we did not only see one such star, we saw a whole group of stars and over time mapped out the beautiful ballet of stars surrounding the central radio source. By now we have about 50 such stars. Some come very close, others not. Some have very elliptical orbits, others actually are more in a plane. It's actually, I cannot explain that in detail, a riddle to us still now, how these stars are where they are. They are very young stars, so they don't have much time to get where they are, right next to the black hole. So there are processes which we don't quite understand. But as I said, nature was good to us by giving us these stars as traces of the gravitational potential and allows us to map this out in some great detail. So after about another 10 years in the mid-2000s, the question was, what can we do to be still more certain? We are certain there's a mass. We know the mass to, about 10% accuracy. That is already pretty good. But must it be a black hole? The same question I've asked before, must it be a black hole? And the answer, unfortunately, is the same. It's likely a black hole. It's consistent with a black hole, but it's not necessarily a black hole. You still have to go closer. And we were relying, when analyzing our measurements, on general relativity to be correct in this extreme environment where nobody had ever made tests. But we knew the star would come back. It's on an elliptical orbit of an orbital period of 16 years, so we knew it would be back in 2018, and we knew if we worked hard, we could perhaps improve our measurements still further. How? Well, where the Chilean telescopes are in the Atacama Desert, 1,000 kilometers north of Santiago, the ESO VLT, as it's called, has 4 8-meter class telescopes. We use so far only one of them, but we have 4. And so our idea was, well, the radio astronomers knew since 60 years you can improve the resolution of a telescope by combining the light of 2 telescopes which are far apart from each other, by interfering the light and then using the interference to increase the resolution. So we said, well, maybe we can do the same. Now it's much harder than in the radio because the wavelengths are short, the Earth's atmosphere is very turbulent. It takes only a millisecond before everything gets, so to speak, the phase gets destroyed. So it's technically extremely challenging experiment which we started back then. But our team, headed by Frank Eisenhower, did it. A team of European institutes and the European Southern Observatory ESO built a machine we call Gravity, where the light is combined in the infrared from the 4 telescopes, and we are improving the resolution and the astrometric precision by another factor of 10 to 50 over what was done before. So we were ready then for the star returning in 2018 and starting to test general relativity. Now, to give you a feeling of how sharp the eyes of gravity is, there's a picture of the moon, and we can resolve on the surface of the moon a coin of the size of a euro cent. So that's about 10 micro arc seconds. That's also the event horizon size of the black hole in the galactic center. And so we started in the beginning of our journey with fairly smudgy images of the central region. You could see individual stars, but not very well. Then we went to big telescopes and used a technique which we call adaptive optics. And then we could show that in this central region, there's a whole cluster of stars right around the position of the radio source Sagittarius A star, which is shown here as a star. So from these measurements over the time of a number of years, we then can derive these motions, which I've shown you in the previous pictures in the movie. But then with gravity, we can look at the center right around the radio point source and resolve that. And the picture from this year, to our great surprise, showed 4 additional stars in addition to Sag A star. Now all on the scale of the solar system, all of them moving very rapidly, all of them being a tremendous set of test particles for the gravitational potential. So it's enormous. We can see the motion from day to day, or within a few months you can see how these stars zip by the black hole, and from that you can infer the gravitational potential and the properties of the gravitational field. So we've come a long way from sort of the first motions, initially of gas clouds, to then of stars, then the orbits of one star, now to orbits of a number of stars, all simultaneously. We see motions not only on scales of years anymore, but from night to night, all with great precision. And that indeed allows us now to see effects of general relativity, which on that scale are smaller than 0.1%, typically about 5 × 10⁻⁴. So there's a tremendous accuracy of measurement. And what do we see? Well, the first deviation from Newton's physics we have seen is called the gravitational redshift. If you have a star like this star S2 float by a large mass like a black hole, then the photons coming towards us have to climb out of the gravitational potential, and that leads to a redshift of the photons, which in this picture below means that compared to Newton's theory, which would be a horizontal line as a function of time, you see there that the wavelength get stretched by about 0.05%, and that is very well seen with high accuracy within our data exactly how general relativity has predicted in this red curve. The second prediction of general relativity has to do with the orbit. We know that, and I mentioned it before, that in Newton's theory we say, well, there's the sun and then the planets are on orbits which are stationary if there is no other perturbation. Not so in general relativity. In general relativity, the prediction is that even if there's only a central black hole and then a star orbiting, that the orbit of this star will precess in forward direction, prograde as we say, over time. Each 16 years, that progression is about 12 arc minutes in the case of the star S2, and we can see this in the data that there is a kink, a change in direction of the orbit very close to the Perry approach of the star. And again, the same situation. The prediction by Newton would predict no effect, while the general relativity predicts a very strong effect in red, and our measurements exactly confirm general relativity. Finally, the object Sagittarius A star is also seen in the infrared, and is a highly variable source. Probably radiation in the infrared comes from very, very energetic electrons in magnetic fields, and these are thunderstorms, if you like. And when that happens, we see the little spots of infrared radiation move around the central position on scales of a few times the event horizon of a black hole, with about a third the speed of light. That's exactly what you would expect from an object like this. So, after 40 years, we've come a long way. We've come from about 1 million times the size of the event horizon. Over time, lots of work, many people have been engaged in this, all the way to the event horizon. And in all cases, we've confirmed essentially the same finding. There is such a mass, and it's only one mass. It's a single object, probably. Maybe there are some stellar black holes, but mainly one mass. And the physics of all of this is indeed what Einstein's theory predicts. So that's sometimes the luck of the researcher. You explore the forest, and then you try to find what nature gives you, and you then have success. Now, we are not the only result in this direction. Andreas' work and my work, which was given a Nobel Prize last year, together with the theoretical work of Roger Penrose, is one of the breakthroughs lately testing general relativity in this extreme limit. Another one is the discovery of gravitational waves in the merging of two stellar black holes. That was done only a few years before and shows us there too the measurements are in excellent agreement with general relativity in this extreme case, but in this case not on a million solar mass black hole, but on a black hole of about 30, 40 solar masses. And finally, the radio astronomers have looked at one of these very bright objects you might almost call a quasar, and found that indeed, as predicted by general relativity, the light in the center, near the object's mass center, is bent such that there is a dip in the radiation, a shadow. And that's exactly what you would have expected. So it's remarkable, all of these efforts have come together about a century after Albert Einstein's work. Now let me finish again and say, are we done? Are we done with our trip through the forest? No, we are not. There are many more questions we would like to answer. Namely, what is inside of the event horizon? What about the singularity? And did these black holes really have an important role in the evolution of our Milky Way and other galaxies? Thank you very much.